Hello, many thanks for inviting me to this event. I will provide a bit introduction about quantum computing, what we are doing in this area at the European Commission, and the potential environmental impacts that this technology will have. My name is Oscar Diez. I am the head of quantum computing at the European Commission in Luxembourg. Before that, I have been working at the European Medicine Agencies in London. I have a university PhD, so my university background is on information technologies. I have a PhD in information technologies, and I'm also an adjunct professor at IE University in Madrid. I will start the presentation with some information about quantum technologies, quantum computing, and the differences with classical computers. I will explore some of the main use cases and applications of this technology with a specific view on sustainability. And I will introduce what we are doing at the European Commission in order to move these technologies from lab to market. So what do we mean by quantum technologies? Basically, quantum technologies exploit the particular effects of quantum physics. So we are now in what is called the second quantum revolution. The first quantum revolution happened during the 20th century and implied that we understood and also predicted the physical processes at the nanoscale level. We're talking here about atoms and even at a lower level. This provided us with things like inventions like chips, lasers, GPS, and a huge amount of different technologies that we use daily now. Now, when we talk about the second quantum revolution, we not only can understand what is going on that level, but we can manipulate and engineer those particles. And this gives us access to even more exciting technologies. Quantum computing is radically different from classical computing, which is based on binary bits that can have a value of either 0 or 1. By contrast, quantum computing is based on the so-called quantum bits, also known as qubits, which can simultaneously have a value of 0 and 1. This is the principle of quantum superposition. By linking together these qubits, or what we call entangle them, the number of states they can represent rises exponentially, making it possible to compute millions of possibilities in parallel instead of one at a time, as a classical computer will do. Quantum computers are quite different from classical computers. So we just say that quantum computers use qubits instead of standard bits. However, quantum computers, the power used by quantum computers grows exponentially in relation to the number of qubits linked together. This differs from a conventional computer, which sees its power increase in direct proportion to the number of transistors. This is one of the reasons why quantum computers could eventually handle some types of calculations much better than what classical computers are already doing. Despite the fact that quantum computers could drastically outperform classical computers at some tasks, such as, for example, optimizing delivery routes or simulating chemical reactions, they are difficult to build, and there are a lot of types of calculations where they aren't expected to offer many advantages. As such, most everyday processing will be better handled with conventional computers, even when that will happen even when powerful computers begin to emerge. Qubits can be physically implemented in several different ways. So using different technologies, and researchers are currently exploring which ones perform better. So we are in what is called the NICS era, or noise intermediate scale quantum devices era, where noise and scale both limit the computations that can be carried out in these computers. A qubit needs to be resilient against noise and also maintains a superposition and entanglement with other qubits for a long time in the face of environmental interactions. A qubit also needs to have fast operations and low error rates, so it is possible to carry out many gate operations with minimal errors. The most advanced technologies at this stage are superconducting and trapped ion qubits, but there are others such as cold atoms, silicon, or photonic technologies that are also advancing very fast. Here you can see some of the main players per technology, but these are changing very often. We are still in a very early stages. At this stage, we do not know if multiple technologies will coexist in the future or only one of them will prevail. The crucial difference is that the ability to compute millions of possibilities in parallel. Quantum computers will be able to perform calculations and solve problems that today will either take many years or are just not possible, even for the faster supercomputers. This means that they will not replace your average laptop or computer for everyday tasks, but they will open up possibilities of which we can barely dream today. For instance, they will be able to greatly reduce the development time of new medicines by modeling huge numbers of biomolecular reactions and then simulating a human body for virtual drugs trials, and run optimization algorithms to solve highly complex logistic and scheduling problems. Also, it will save time and fuel, or will permit finding the cheapest combinations for renewable sources to supply an energy grid. Those are just some of the numerous examples, and there are probably more that we haven't even imagined yet. As with classical computers, on top of the hardware, we will have all the electronics, including the quantum compiler, the programming languages, and the algorithms that you will run. There are different software development kits currently with standard languages such as Python, for example, and many online platforms today, normally cloud platforms, that everyone can use in order to learn how to program these quantum computers. When programming, the quantum programs can be represented as circuits. We see an example here of a circuit and an algorithm. These circuits will execute specific operations done by what we call quantum gates on the specific quantum qubits. In the near to medium term, quantum computing will provide benefits in three main areas. One is quantum simulation, another is quantum optimization, and quantum-assisted machine learning. The list, however, the list of categories that will be directly impacted by quantum it's very big, include things like, as you can see there, physics, chemistry, mathematics, biology, just to say a few, and also all the applications that you will be able to use for industry, and the way it will impact some industries, specifically some verticals such as healthcare, for everything that we were saying about the drug trials, finance, commerce, communications, security, cybersecurity, and cryptography, energy exploration, and many other disciplines. So it could help a lot of different disciplines. In much shorter time frames, they will be able to process far larger problems while consuming also a lot of less energy. That means, for example, that they will play an integral role in the development of new medicines, or for example, screening millions of 16 molecular compounds to find a promising treatment, and then simulating human bodies in order to conduct virtual drug trials that could short radically the time needed to bring a drug to market. Quantum computers will also be able to run optimization algorithms to solve highly complex, specifically logistic and scheduling problems. For example, enable companies to save time and fuel, for instance, or finding the cheapest combination of renewable sources to supply an energy grid. Those are only two examples, which are especially striking given today's news agenda, but there are many more, including, as I said before, some that for the moment we didn't imagine. Even over the long term, quantum computing will not, as I said before, will not likely replace existing supercomputers or high-performance computing. Also, even if they are not going to replace this type of computers, now there are some attempts to try to integrate them with the supercomputers in order to solve full problems and try to help the way the current supercomputers are working. What we believe is that successful quantum computers use cases will, at least for the moment, rely heavily on what we call hybrid solutions, at least over this decade. First, basically a small quantum computing or subroutine will generate a rough answer for an optimization problem. It will not be the exact answer, but it will be a very approximate solution to the problem, and it will be extremely fast. A conventional HPC normally will refine this answer with a narrower set of variables, and in this way, programmers can employ early-stage quantum computers to run HPC more efficiently and run things that will take days or even weeks to run in seconds using the help of quantum computers. Another very promising application is sustainability. The two most relevant areas where quantum computing could play a key role on sustainability are first the efficiency of the systems in terms of energy utilization. We know that quantum computing will not replace, as I said before, classical computers, but quantum computing will improve dramatically the performance, especially on certain use cases where classical computing is currently used. Basically, supercomputing is moving now, as you know, into what is called the exascale era. We have now some exascale. We have one exascale system, and more are coming supercomputers. This means normally more than 20 megawatts of power from a supercomputer. This is a huge use of energy for these supercomputers. Just to give an idea, quantum computers could help to reduce drastically the energy consumption, while at the same time increasing performance. In some cases, with up to 1,000 times less energy consumption than a standard supercomputer. The second and probably bigger area on sustainability for quantum computers is basically the discoveries. I've been talking about that in the previous slides, the discoveries that quantum technologies will allow. So not just in terms of energy efficiency, but more generally in terms of resource efficiency and greenhouse gas emissions. So for example, improve models, better predictions, and improve mitigation plans to deal especially with climate change, or use greener technologies such as more efficient solar panels, better batteries, more efficient ways to produce, for example, fertilizers, and more efficient transportation and optimization of routes and processes. Quantum computing could also bring changes throughout the economy that will have a huge impact on carbon reduction, including by helping to solve persistent sustainability problems such as curbing the methane produced by agriculture. So making the production of semen emissions free, or involving electric batteries for vehicles. Also, another example will be developing significant and better renewable solar energy, finding a faster way to bring down the cost of hydrogen to make it viable alternative to fossil fuels, and using green ammonia as a fuel and a fertilizer. McKinsey projected in one of the recent studies that by 2035, the use cases listed there in the image could make it possible to eliminate more than 7 gigatons of CO2, that it will be an equivalent to the atmosphere from the atmosphere a year, compared with the current trajectory, or aggregate more than 150 gigatons over the next 30 years using these technologies. But one question is that we always get is, are we there yet? And as an example, I want to start with the image that I have. You can see there. So this is in 1830, a race between a steam and a horsepower that basically marked the moment when the Industrial Revolution changed the transportation forever. On that race, by the way, the horse won, as the locomotive was unable to finish the race. But we all know who was the final winner. So we see often very optimistic and pessimistic articles about quantum technologies. I personally believe that quantum technologies are here to stay, and we can see the progress now with the number and also fidelity of the qubits. We see how they are evolving. It's starting to be more an engineering problem than a research problem. So we know how to achieve it, that now we need to engineer it. And the question is not if they will work or not. This has been further demonstrated, but when we will have world-changing applications in our everyday life. So it is probably true that currently there is also a hype, and so in some cases the timelines are shifting, but it's also true that we are starting to see the potential realize. As I will explain later, we are starting to install, for example, as an example in Europe, multiple European quantum computers that currently are being commercialized. So you can buy them and you can install it and you can run it. So I normally try to say that we are now we can compare it to what if the IT industry was 50 years ago. But of course, the changes are a lot faster now. So we are seeing that from one year to the other, there is huge differences. At that time, 50 years ago, in the IT industry, it was very difficult to predict dates or even imagine achievements like the internet or the smartphones with the technology that they have at that moment. According to there is a quantum technology readiness level that it was created by Jülich in Germany, where basically the level 9 means that the quantum computer exceeds the computational power of classical computers for general problems. According to this scale, we are now at level 5, where the primary obstacle is to overcome the error correction. Basically, the quantity of errors that we have in the calculations in the qubits. This does not mean that we cannot use these computers yet. We are, as I said before, in what is called the NISQ era, or the noise intermediate scale quantum era, where quantum processors contain about between 50 and a few hundreds qubit, but they are not advanced enough to reach what is called the fault tolerance, so basically not to have these error corrections. And we will, for the moment, we cannot profit from quantum supremacy at that stage. But as I said, currently the technology is moving very fast, and some researchers predict that we will arrive to level 9 before the end of this decade. So let's see what we are doing here at the Commission on this area. I will start providing a bit of context. So in the European Commission in 1999, the EU was the first region in the world to launch a public research program in quantum. In 2016, 4,000 of our researchers endorsed what we call the Quantum Manifesto. Basically, was defining a common strategy for Europe on quantum technologies. And this enabled, 2 years later, the creation of the Quantum Flagship. That it was basically a 10-year initiative with an approximate budget of 1 billion euros. The aim of the flagship is not only to support research in quantum, but that is one of the main goals, but it's not only that, also to transform the results of this research into industrial exploitation and real-life applications. The flagship is, as I said, is a long-term project, but we have already excellent results. In fact, the most successful quantum computing platforms that are currently in Europe started as project of the Quantum Flagship. And this, of course, has permitted to launch as part of one of the programs that we have in the European Commission that is called the Digital Euro Program, different initiatives that will permit the deployment of quantum infrastructures in Europe, so researchers can use those infrastructures. It is important to explain that even if this, I'm talking here about quantum computing, in the Commission we are covering different, what we call pillars of the quantum technologies. So although quantum computing is very high in our agenda, we also work in other areas that are very important, such as quantum simulation, quantum communications, quantum sensing and metrology, and other aspects such as basic science or digital skills. At the European Commission, we have a long-term vision of all the quantum technologies areas, and particularly on quantum computing. One important concept in quantum computing is the fact that currently there are multiple architectures, as I said at the beginning, for the quantum processing units. Basically, it's like imagine that we are at the beginning of the classical computing era, so when the IT started, and in that case, we have like 8 different ways of implementing microprocessors. So we are more or less in the same case. We don't know, even if the software that you have running on top of those quantum computers will be similar, each architecture currently at this stage have pros and cons, and currently they are not clear winners. We are working, in our case, we are working in different architectures, being the 2 main ones that we are using is trap ions and superconducting qubits. Superconducting qubits are the ones that are also used in other companies in the world like IBM and Google. But we have also projects in silicon semiconducting qubits, and so we will include other projects, other platforms like, for example, photonics or NV diamonds. We are working not only on the hardware and the control layers, but also on the software layers. And I will talk about two of the projects that are currently being funded. So one is Axiom project. A company has been created. It's called AQT, and basically this company has produced a compact ion trap quantum computer they are based in Austria. And these quantum computers are provided as a standard, normally the 19-inch racks. So it's the standard racks that you have in any data center, and they operate at room temperature, because this technology is not, they basically can operate at room temperature and can be installed in any data center. This quantum computer has currently the world record of full entangled 24 particle quantum state. And currently they have they are developing, they are doing a 50 qubits upgrade for this machine. The second project, it's a quantum computing platform that is called Open SuperQ, and this is working in the full stack of the superconducting quantum computing. The development here includes not only the quantum hardware platform, but the whole software stack and the control electronics. And by the way, the pictures that you see there, that looks like a chandelier that you will see in most of the supercomputers, so in most of the quantum computers, that are using this type of technology is a refrigerator, is a cryogenic refrigerator. Basically, the material they use in the quantum unit, they use for the superconducting, in this case superconducting, we need to bring it to close to 20 millikelvin, or what is like minus 273 Celsius degrees. So it basically will be one of the coldest places in the entire universe. And we also, as I said, we are also working in the software side. In the software side, we have multiple projects. So one of these is NEASC. It's a project for developing quantum computer software and applications, and they are based they are used, basically, they are always focusing on specific use cases. And the focus here is to develop new applications that can take advantage of the existing quantum computers, what we call the NISQ, noise intermediate scale quantum computers that we have now. And it is centered on industrial cases that and is producing, basically what they are doing is also producing programming libraries, and they are both developing both the software stacks and also benchmarks that can be used to benchmark different quantum hardware platforms. As part, for example, of that project, one of the applications is a quantum rule-based system that is used for breast cancer detection. And this is a problem that we have currently with this type of rule-based system, is the great sensitivity to the number of hypotheses, data, and rules of the system itself. So, for example, when selecting, you need to select which rules are applicable at each moment. Can be basically slow down the inferential process. And for this process that is called pattern matching, is one of the currently unresolved issues in artificial intelligence. And this is here basically in with this issue is that quantum computing, with basically the parallel nature that you have on these quantum computers, will be useful for artificial intelligence in general, and in particular for this type of problems with the rule-based system. A key infrastructure initiative is focusing on the deployment of quantum computers and simulators in Europe, together with the Euro HPC supercomputers, Euro HPC JU, that is responsible of setting up deployment of supercomputers in Europe. Basically, this project, that is the quantum computing and simulation infrastructure, will involve the deployment of integrated HPC and quantum computers. So what we are doing is procurement and deploying quantum computers together with the supercomputers and doing all the integration. We currently have 2 quantum simulators from the French quantum computer company Pascal that has been installed. And we just announced the results of the selection of another 6 hosting entities that will deploy quantum computers integrated into the supercomputers, all based on EU technologies. The domain of quantum computer, as I said, is still emerging, and it's not clear what kind of technology will be the best for building efficient and functional computers. Therefore, the quantum computers will be based on, in this case, these 6 quantum computers that will be installed will be based on different promising technologies. As I said, all of them developed in the EU, and they will be available for academic researchers and industry anywhere in the EU. They will help these users to mature further, the technologies further also, and we will plan for new markets and attract further investments on this technology. The idea here is to accelerate the development of quantum computing applications that will solve basically real-world problems. The first initiative is called, the one that I was saying before, is called HPC QS. And will involve the deployment of quantum computers and quantum simulators, with doing also, as I said, the interface with the supercomputers from the Euro HPC. And these deployments include not only the integration with the classical HPC systems, focusing not only in the hardware but also in the software stack, and also with doing real use cases with the industry. But as I said, this is not the only area we are working here at the EU in order to have a healthy quantum ecosystem. One of the main problems that we see now for the success of quantum technologies is this lack of a skilled workforce. There are similar problems in other areas in other regions in the world, and this is key. This is key to invest in quantum education for both students and workforce. So we are working in the creation of one of the things that we are doing is a European master program, quantum technologies, for all European universities. Also, recently we have published a new competence framework for quantum technologies that aims to map the landscape of possible competence and skills in quantum technologies. And we have also a pilot program to implement a reform approach of both formal and informal quantum technologies learning in selected member states for universities, high school education, and also for the industry, for the quantum industry. But this is only the beginning of a long journey, not only on quantum computing, but other areas where we are working, such as quantum communications, with the deployment of a European quantum communication infrastructure, quantum sensing and metrology activities, also the creation of quantum technologies fund, or the scale up of the quantum manufacturing facilities with the inclusion of the quantum into the CHIPS Act. We need to increase basically our efforts to move from what we say from lab to market, to being able to achieve the full potential of these quantum technologies. And with this, I finish my presentation. If you would like to know more about the technologies and what we do, you can follow us on qt.eu. And thank you very much for your time and for the invitation.